discussion of the hydrogen-like system, we understand the motion for the electron, that one electron in either the atom or ion. And we show the wave function to describe such system can be separated into the radial component, depends on the radius variable, and also the angular component. And we already saw for the angular component, that is your particle rotation on the sphere. So it depends on two variables, theta and phi. And then you have the radial component. So the total wave function for the orbital motion for the electron in the hydrogen atom is the product of those two components. And we have three quantum numbers to satisfy the boundary condition among those three variables. So we have quantum number n, l, and m-L. All right, and then toward the end of the lecture, we show the solutions. My ink. The solutions for the energy. It is a negative sign. That is due to the attractive interaction between the electron to the nucleus. You have a bunch of terms. You have a bunch of terms regarding with the constant. Then you have z values, because we're looking at one electron system that can be hydrogen atom or ion, right? And then the energy depends on the principal quantum number n. So that refers to, immediately comes to the mind is you have three quantum number to define the quantum state. However, the energy only depends on the principal quantum number, so we have this degeneracy. And we said the degeneracy is n squared. Okay, now we can plug in those constant values, okay, and then we can introduce the Rydberg constant. All right, so there are two writings of the Rydberg constant. This is the Rydberg constant that indicated here. This one is the Rydberg constant related to a particular atom, but they are related, those two. All right, so you can group a bunch of constants, substitute it with the Rydberg constant. That's about it. All right. And then if we really look at the simplified version of the energy for the electron in the hydrogen or hydrogen-like system, you have a negative sign right here, and you have a constant, and then proportional to the z squared, and inverse proportional to the quantum number. All right, now we say the principal quantum number can take positive, they are positive integers. So as you can see, when n approaches to infinity, then the energy at the infinity approach to zeros. All right. Otherwise, it's a negative value. All right. Now, we're always interested in the ground state. Ground state is really the quantum state that has the lowest energy for the system. So for this particular, for the hydrogen atoms, what is our ground state, guys?
Ground state is.
Then you look at the energy expression. At which value of n can give me the lowest energy value? When n
Infinity.
equals to?
Infinity.
So remember, it's a negative sign. You have a positive constant, and then you have z squared, which is positive, divided by n squared. So it's a negative value. So the lower the n is, the more negative the energy value is. You guys agree with that?
Mm-hmm.
So therefore, the lower to state is when n equals to 1. All right, when n equal to 1, what would be the quantum state? So we say we need to have three quantum numbers to define the quantum state, n, l, and m sub L. So therefore allow us to decide the wave function. Right? Once we know those three constant states, allow us to define a wave function using the table I showed you guys a moment ago. We can write out the exact expression for the electron in a hydrogen atom. So if n equal to 1, what would be our L value?
Yeah, let's
N would restrict the value for the L. L will restrict the value for the n sub L. So when n equal to 1, L equals to 0. Only 0. Then m sub L 0. Only can take 0. So therefore the ground state will be the psi 1, 0, 0. Okay, all right. Now we'll come back to this, but that is our ground state with the corresponding energy value of E sub 1. Then you plug 1 in replacement n with 1, you put all the constant, you put all the z value, you get a value for your energy. Okay? Alright. Okay. Now, if I wanna, that's a general discussion for the electron in the hydrogen-like system, just one electron system. Now what we're going to is that we are going to apply to the hydrogen atom. For the hydrogen atom, then from a generic, guys, from a generic z squared here, hydrogen atom, we know the z value is 1, so you can plug 1 into it. You can derive the expression, the energy expression for the one electron system for the hydrogen atom, and that's where you have it right here. You can write out with the exact constant as you wish as starting point, or you can substitute with the Heisenberg constant, which substitute some of those constants right here. So therefore, the energy expression for the hydrogen atom equals to, now if we have a z equal to 1, you're looking at the hydrogen atom system or the electron in the hydrogen atom, right? So that's our system. Your particle is your electron in the hydrogen atom. Okay, so then the energy for this guy then equals to Hc, the Heisenberg constant for the hydrogen atom, and then it depends on the quantum state because the electron can be in various quantum state defined by n sub L. Then energy is dependent on that quantum state, specifically the principal quantum state. So this just tell you the energy for the electron in the hydrogen atom is also quantized, can only take certain discrete values, not a continuous value. Okay, now the H here is the Planck constant, C is the speed of light, and this is your Heisenberg constant for the hydrogen atom, which equals to 109677 per centimeter. Okay. All right. Now, for those of you who want to try out, you can calculate this constant right here and see if it matches with the Hc time divided by constant. There's really nothing fancy, just a substitution. Okay, now I can draw an energy diagram as I wish, right? So I can represent this whole thing in terms of the quantum number n, and starting with 1, 2, 3, and then go all the way to the infinity, and then you have axes for the energy, right, corresponding to the n, right? So, and then we know when n equal close to, approach to infinity, what will be the energy value, guys, approach to? When n approaches to infinity, what will be the energy for the electron approaches to?
0.
0. So therefore, if I want to write out right here, what do you write 0 right here, right? So therefore, instead of a number, we're just using a line to indicate the values, like this. Right, so corresponding to n equal 1, 2, 3, 4, so on and so forth. All right, now the one question is, what about the emission? I can have an electron hopping from one quantum state to another quantum state, right? So let's say, let's say electron at this particular quantum state. I want to hopping back down to this particular quantum state. What spectroscopy are we talking about this? Right? So with electron, particular system, here the system is electron in a hydrogen atom, hopping from one quantum state to another quantum state. In this particular case, we're talking about absorption and emission spectroscopy. So we can look at the electron emission spectroscopy for the hydrogen atom or absorption spectroscopy. So what I'm saying is, if I'm looking at specifically in this case, hopping from here to the ground state or to the lower state, what do you guys think? Is it absorption or emission?
Emission.
Emission. Okay, why is that? Yes.
It's losing energy now.
Yeah, so emission is coming from where? The higher energy level to the lower energy level. So therefore, the excess of the energy will be reduced, emitted as the photon, right? That is what the emission spectroscopy is. The system, transits from the higher level to the level. Now, what about the extra energy differences between the two? That will be emitted as a photon. Now, if the system hopping from the lower to the higher level, what would happen? It needs an external energy input. The external energy input is the light coming in, make that transition. So it doesn't matter, transit from high to low, low to high. But if it's from higher energy to the lower energy indicated here, then the excessive energy for the system will be released as photon. Are you guys follow me, okay? So therefore, the delta E from the system, the difference is the energy from your final state minus the energy from the system from the initial state. That energy has to be matched with what? The energy of the photon. That's a Bohr frequency condition. Now, because this is emission, we just put absolute. We just want to know the differences in the energy for the system matched with the energy of your photon. So you guys follow me, okay? We're talking about transition for vibrational motion. We're talking about transition for translational motion, and this is just the spectroscopy for transition for electrons in a particular two quantum state. Now, because the initial energy is higher than the final energy due to the emission here, so let's put an absolute. All we care is the energy values. They match to the energy of the photon. Okay, if that is the case, now what we can do, is, you guys can go home to do it, or I can go through with you guys. Now we can do is right here. We can even derive the expression. So the energy of the photon that is released has to equal to the differences between those two quantum states. Because it's an emission, it has negative value. Just the magnitude of the energy differences has to be the same. So I put an absolute value. Now the energy of the photon, what you need is equal to the Planck constant times the frequency of the light. We can convert it to the frequency. wavelength, or wave number. So in that regard, by setting those two expressions together, suitable frequency condition, we can, guys, predict what frequency of the light is needed for the electron in hydrogen to transit between two quantum states. That's about it. So you guys follow me, okay? Because we have a generic expression, we just plug in those two in. Okay, now let's do an example. What kind of transition would you guys like to have? Should we try with how about this? Can we transit from n equal to 2 to n equal to 1? We can do that, right? Alright, now let's calculate the delta E. What will be the delta E? Then your final state is if when the principal quantum number equal to 1, your initial state is n equal to 2. Any questions on that? I didn't do anything, I just write it out. The delta E for the system for the hydrogen atom transit between two quantum states from the hopping from n equal to 2 to the ground state n equal to 1. And then the differences is your final minus the energy for the initial. All good? Okay, now what is our general expression for the energy? We can hopping back. Alrighty, we can hopping this back. So therefore, the energy for the hydrogen atom equals to the Hc Rydberg constant for the hydrogen atom, then 1 over n squared. Does that make sense? We know what the Rydberg constant is. Equals to 1.677 per centimeter squared. Okay, so now let's plug it in here. So in that case, the first term is referred to the electron in the ground state, okay? Which means that n equal to 1, so therefore I have a negative Hc, like constant, speed of light, the Rydberg constant times 1 over n squared, n right now equals to 1 squared. Any questions? Okay, now what we have is minus the initial state, that is n equal to 2. So therefore, you do the same. Does that sound good? Okay, now we can combine the terms. How can we combine the terms? Hc off, Rydberg constant, they're exactly the same. So you can take that one out. So you're going to have Hc Rydberg constant. Then what do you have it here? Negative 1 plus plus 1/4. Any questions on that one? Okay, now what will be this right here?
Negative 3/4.
That would be times what? Negative 3 over 4. The negative sign here is just to tell you the energy is released. Right? Isn't the energy is released? Okay, alrighty. Now, how I'm going to know what frequency of the light will be released? Then, the energy differences from your hydrogen atom, which equals to negative 3 over 4 Hc Rydberg constant. I don't particularly care, I already know it's an emission, so I just want to know the magnitude of the energy is that much. Okay, and that equals to the energy of the photon. That differences in the energy for those two quantum states will be released as the light. So therefore, whatever the difference will be directly equals to the light that is released. Okay, now that is a light. The light we can calculate in terms of what? Frequency of the photon? Or we can calculate in terms of the wavelength of the photon? Or we can calculate in terms of the wave number of the photon. They are the same. Now how do? We will measure in our experiment. How many of you do the UV vis? That is exactly what we're looking for. For the UV vis, we're looking at the transition for the electrons in a particular system. Okay. All right. Any questions on this? Okay. Now, in Gen Chem, in general chemistry, you guys come across ionization energy? Okay, what is the definition? What is the definition of ionization energy in an atom?
Steam.
Or hydrogen atom, let's say. What is your definition for the ionization in a hydrogen atom?
It's the amount of energy required to knock the electron away.
What? Go ahead.
It's the amount of energy required to knock the electron off of the hydrogen atom.
Okay, knock it off from hydrogen, more specific. Because now the electron can be in many quantum state. So how do we define that? It's good though, that is correct. It's the amount of energy to remove the electron from the hydrogen atom. But that electron can be in many of these quantum state. What specific quantum state is referred to the ionization? Remove from which state?
Ground state?
Yes, who said that? Okay, removed from the, so the ionization energy is really the amount of the energy that is required to remove the electron from the ground state. The ground state. Okay, so from the ground state, remove it totally, like, okay, how should I draw this? So just like knock this one out, totally out that electron. So the ionization energy is the energy that required to remove the electron from the ground state. Now, how do we calculate this? All right, so sometimes people use the IE to refer to the ionization energy, fine. But so if we remove from the ground state from the atom, so remove from some state to some state. So the initial state is the ground state. You guys agree? Is the initial state the ground state? How about the final state? We should remove from the atom. What does that mean?
An infinity?
The end really what? Approach to infinity. It's away from out of that atom. So the final state, you're really looking at the end wall. Oh, I should say the initial state is referred to the ground state, which means n equals to 1. Then the final state, you're really looking at when the n equals to infinity. And that is your ionization energy. So the ionization energy is really the differences between your final state versus the initial state. Now, the final state is when the quantum number equals to, look at the energy diagram, right? So the more aware from the ground state is approaching to infinity, then minus the energy of the electron in the hydrogen atom, then when n equal to 1. So what would be the value when n equal to infinity, guys?
0.
0. Very good. And then your ground state is just E sub 1. So therefore, your ionization energy just equals to what? The negative value of the ground state. What sign is that? Positive, negative?
Positive.
Huh? Positive, right? So therefore, you take it, and it makes sense. It takes energy to remove the electron from the atom. So that is your positive value. Alrighty. Now, one more step. We can have the energy in terms of the joule, which is your SI unit, or we can calculate the energy in terms of the electron volts. That's what it's showing you right here. So electron volts can be converted to joules, right? In some spectroscopy group, they like to use wave numbers to infer for the energy. But nevertheless, we can make our life easy if you put all this constant together. Alrighty, so I just want to show you. I mean, you can go home and check it. So this is your general expression. If I substitute with the Rydberg constant to be equivalent to this, hold on, give me 1 second. Okay, so this is your general constant right here. If you substitute with the Rydberg constant for the hydrogen atom, they should be equivalent. Okay, now you can try. All right, now you can write in terms of this generic as you wish, or in terms with the Rydberg constant. But nevertheless, if you put all the constant number into it, that actually equals to 13.6 electron volts. All right, so that makes our life so much easier. All this constant for the hydrogen atom, that equals to 13.6. So therefore, this will equals to what? The ionization energy for the electron in the hydrogen atom, that equals to the negative of the ground state energy, and ground state energy equal to that value when n equal to 1. So the ionization energy for electron in the hydrogen atom equal to 13.6. But I don't need you guys to remember. I want you guys to know how that works. It's really the differences between the ground state versus the n equal to infinity. And you put those two together, that's what you're going to get. Okay, alrighty. Okay, now if we look at the hydrogen emission spectroscopy, atomic spectroscopy, right? We can talk about spectroscopy in terms of absorbing light or releasing light. Then we can separate into the absorption or emission. But we also can talk about spectroscopy in terms of whether it's related with the atom or related with the molecule. So we can have atomic spectroscopy or molecular spectroscopy. Here we're looking at the spectroscopy related with the transition of the electrons in the hydrogen between different levels. Alrighty. Do you guys remember this in your gym camp with this spectroscopy? I think so, because I just taught Gen Chem 2. Maybe, okay. Now, have you guys heard about the emission spectroscopy for the hydrogen atom? Has a Lyman series, Balmer series. I can keep it going. Just to show you here, now you know I'm joining here, okay? Now, what is the Lyman series? Is the emission spectroscopy. Okay, if you're gonna take a look at this diagram right here, tell me, what is the Lyman series?
where an electron is performed from outside the atom all the way to the ground state?
Excellent. All the transitions goes to what? The n equal to 1 state. Can you guys see it right there? It's an emission spectroscopy, so from higher quantum state goes to the n equal to 1. Now you have a lot of them, do you agree? You have a lot of them, okay? Now how about the second one, the Balmer theory? That is, all the transitions goes to n equal to 2. Very good. Okay, so yeah, and then you can keep it going. And did you see why they have a different color right there? Yeah, because the energy differences that equals to the energy for the photon, so therefore the emitted light in a different spectrum, so they have a different color. Okay, now previously when we learned from GenChem, we just said, okay, this is the Lyman theory, this is the Balmer theory. Now we can tell them exactly what the nature of this one, and we can even tell them what the frequency, what it is. Because if I know from n equal to 2, go back to n equal to 1, not only I know it is a Lyman theory, but I also can tell at what wavelengths I would observe the emitted light. Are you guys following me, okay? All right, okay. Alrighty, now here on the right side, let's just go back to the question. As you guys can see it, the transition going to take place, or the light emitted will occur in the UV bits, or some of those in the UV bits. Okay, now we say the Lyman theory is transit to n equal to 1. Then Balmer n equal to 2. But the quantum state for the electron is determined by 3 quantum numbers, not just principal quantum numbers, but by 3 quantum numbers. All right, so not all quantum number transition with all quantum numbers are allowed. This is a spectroscopy. I know it's another level of a discussion. We're not going to go to the depths of it. Hope some of you in the future, when you go to graduate school or something, take a spectroscopy class based on quantum mechanics. We will go to the depths about this. We will have a selection rules. The selection rule will tell you, during that time when you study, it will tell you exactly why certain transitions are allowed. So that is called the selection rule. Remember we're talking about harmonic oscillator? Harmonic oscillator, when you have vibrational transition, there's a selection rule between the delta V equals to plus minus 1. Now for the hydrogen atom right here, the selection rule. What is the selection rule for emission spectroscopy right here, guys? The selection rule? Oh, I thought it's on the slide, no? What is the selection rule? I'll tell you. Huh? Delta L equals to plus minus 1, and then you have m sub L equals to 0, change. Delta m sub L equals to plus minus 1. Okay, let's give it a shot. Do you guys think the 2s, sorry, I won't do 2s. Do you think I would do how about this? I'll do a 2, 0, 0 quantum state. Okay, let's write it out nicely. With the quantum state 2, 0, 0. Do you think in the transition to the quantum state 1, 0, 0 is allowed? Now we need to check the transition rules. which means the delta L, right, it's between your final state to the initial state. Now, what is the L for the initial state, guys? Initial state is from 2, 0, 0 to 1, 0, 0. What it will be the L value for the initial state?
2.
0.
Hmm?
What about the final state? 0. Now, what is the delta L?
0.
Do you think that transition is allowed? Yes or no? It won't happen. That won't happen. Okay? Although it is higher to low energy, but it will not happen. You're not going to observe any light emitted from this. Now, guys, if I want to make a change for this, what would I change that will make it allowed? Did you guys say 1? Would that be allowed? Then let's evaluate this. So the initial state will be L equal to 1. The final state is 0. This corresponding to N L epsilon L, right? Those three constant states. Yes, yes, yes. Okay, so this is your the final. Oh, that is your final. It doesn't really matter which one. This is your final. This is the initial. So therefore, this is your initial. L equal to 1 is equal to 0. This gives you -1. So what do we satisfy? We satisfy with the selection rule regarding with the delta L. How about the delta M then? Epsilon L. It's from 0 to 0 equal to. Does it satisfy the selection rule? Does it satisfy with both selection rules?
Yes.
So do you think that transition will be allowed? Excellent, excellent. And then you can calculate for that to happen. We know the energy expression, you can calculate what will be the frequency for that transition. Okay, very good. Okay, so we have a quantum mechanics discussion with the electron in the hydrogen light. We're bridging to the hydrogen atom. We show you the sum of the properties, including the spectroscopy transition emission. We show you the ionization energy, right? You can calculate that. And we have a lot of things we can calculate. For instance, what about the probability to locate that electron at a particular quantum state? What about the angular momentum values as the electron orbit around this nucleus, right? There's so many things we can do. So what I'm going to do is, I'm going to use the one particular problem, and let's walk through some of those properties. Okay, I'm going to using the quantum state for the ground state as our example. And let's walk through some of these calculations. All those calculations, guys, all based on the postulates you learn. That's your foundation. Plus, of course, you have to utilize the wave function and energy expression from that electron in the hydrogen atom system. So that is a combined. Which one do you guys want to go first? I told some of you guys we need an hour, 20 minutes lecture to go through the whole thing. Which one you guys want to go first?
Just start at 1, I guess.
Number 1? Okay, all number 1? Okay, very good. Okay, so write down the wave function for the electron in the 1s orbital, which give it to you. Define that is the C100. At which point does the probability density for the electron in the 1s orbital has its maximum value? So let's right away, what is this asking you for? It asks you the probability density. The question asks you the probability density. Now immediately from the quantum mechanics, I know the probability density is the square modulus of the wave function. That has nothing to do right now, it's just a generic definition, right? What else I'm gonna ask you more is I wanna get the, so if I wanna write out, if you write this one out, I probably already give you 40% of the points, because that's literally is asking you the probability density and finding maximum for that probability density. Now we need to look at it. What I'm looking at is the hydrogen atom. So therefore, I need to get the exact expression for that wave function to figure out the probability density. Okay, now the wave function is 1, 0, 0, guys, with r, theta, phi, 3 variables. Now how am I gonna get that expression? How am I gonna do that? What do you guys need? How do we need a number to it?
The charts.
The chart. Okay, great. Table, right? Is that the table?
Yeah, table.
Okay, great. Alrighty. I assume this is the table you guys are looking for. True?
Yes.
Is that the table? Okay. So tell me now the wave function for the electron in the hydrogen atom, it contains two components. The radial component depends on the principal quantum number n and the angular momentum quantum number L depends on the radius and the time. The angular component that has the two quantum number L and n sub L depends on the two variables. So I need to split because that's how we go through. I walk with you guys through in length of depth, so we understand how we conceptually get this. Alrighty, now L and n sub L for this particular problem is 0 and 0, right? Yes. Okay. All right. Can we plug in here now? So I have a 2 for the radial component, z over a, 3 over 2 times e raised to the rho divided by 2. That's my radial component of the wave function. Then I need to time the angular component. What is the angular component value here? Huh? The
1/4.
Yes. Okay, but they give you the expression in terms of rho to make the expression easier to show. But the variable is really what? The radius, the theta, and the phi. So therefore, I'm going to substitute the rho here. Alright? So what is the rho here? Rho is the definition of 2 times z times the variable r divided by NA. Okay, now we're looking at this particular system, the question that I have, the ground state for the hydrogen atom. All right, now how are we going to substitute? 2 times z equals to 1, then r is my variable, divided by, what is n value here? 1, because I said this is my ground state and it's 1, so I substitute the 1 here and then time the A. Any questions on that? Alrighty, so therefore I can simplify this as, for the ground state hydrogen atom, this will be 2R over A. A is a constant. I won't worry about that right now. A is a constant. Okay. Alright. Then what do I need to do? Guys, I need to substitute the rho here. Okay, so what I'm having here is 2 right here, nothing. for hydrogen atom, Z equals 1, so 1 over A, 3 over 2 times e raised to the power of negative rho divided by 2. If I substitute the rho right here, what I'm going to get? It's the negative R over A, then time the constant. That's the wave function. That's the wave function, guys. Okay. Any questions on this one? Alrighty. Now, for this particular wave function, although generically the electron in the hydrogen-like system depends on 3 variables. However, when the L equal to 0, and sigma equal to 0, then the angular component become a constant. It doesn't matter what the theta, what the phi angle is. All right. So therefore, if you evaluate this mathematically, only depends on what? The radius. The wave function for the ground state electron in the hydrogen atom only depends on the radius. Okay. Now, this is your wave function. Now, we come back to the question. Alright, now how are we going to find the maximum for the square modulus of this wave function? How are we going to do it? Then we need to evaluate. And sometimes you want to find the maximum if you do what in the inversion is what equal to 0, if the substitute inflection point. Or for this one, I think I just can eyeball it. Why can I eyeball it? The wave function depends on the R. R is an E function. It's an exponential decay, which means as you're increasing the R from 0 to infinity, the wave function value decreases. So therefore, the maximum value for that wave function is at R equal to 0. So sometimes you can use that's where the math kicks in. So you have a specific function. How can you find the maximum value? Now, of course, I'm looking at the wave function itself, but the square modulus is exactly the same. Why is that? Because this is a real function. You take a square, still the exponential decay, everything is the same. You guys follow me, okay? Okay, all right. Now, okay, let's see. I have, how many minutes do I have?
2.
2 minutes? Okay, you guys choose one, then we will go for that. No more. Alright, how about let's do the average value for the radius? Like, we can calculate the average value. Now, how do we do average values, guys? Average value, or we can call it
Expectation.
it's also the expectation value too. So right away, you're going to use the quantum mechanics, the postulates, and think about it, what I'm going to do, right? So how do we do the expectation values, guys? If you have a observable of interest, and then you have integral of the contrast conjugate for that wave function to define the quantum state, and then time the operator for that observable, operate onto the wave function, integral with allow the space, and then you have the denominator. Okay, now if the wave function is normalized, they make our life easier. This whole thing will vanish to 1, right? That's the definition of the expectation values. Now, if I'm interested in the radius is the position operator, right? Well, here, x, y, X, Y, Z is a position operator. That is in Cartesian coordinates, but in the spherical coordinates, they're corresponding to r, theta, and phi. So therefore, how can we come up the operator for the position?
It's just R.
So it's the variable for that position, and it is a multiplication. All right, so we will pick it up from here, but I do want to check two of you on Wednesday, see what you guys come up with the answer. Give it a try. Okay, or set up the expression at least, all right? Okay.